Hi, my name is Hadi Sadati from King's College London. Today I present stiffness imaging with a continuum appendage, real-time shape and tip force estimation from base load readings. Our research questions and contributions. The questions are if we can do a stiffness imaging with a continuum probe and comparison versus a rigid one, and what is a reliable, accurate, fast method of a stiffness estimation if we use a continuum probe. The contributions are the application of a continuum appendage for stiffness imaging and introducing forward integration of Koszorot rod theory based on base force reading. Our experimental setup. We use a stiff flop appendage as a continuum probe. We have base force sensor, which is used in the simulations, and we have a tip force sensor, which is used only for experimental validation. We have a phantom tissue fixed on a linear actuator in which we embedded a hard nodule, and the slider moves from right to left underneath the appendage. A stiff flop appendage is a pneumatic actuator with silicon shell. It has 3 pairs of pneumatic chambers braided and placed with an offset with respect to the center of the appendage. And the silicon phantom is a cube with an M8 knot embedded as a hard nodule in it, and we probe directly on top of the knot. Continuum appendage static model. We start by assuming that we know the base position and orientation because it's fixed, and moments and forces because we have a force sensor there. We use variable curvature kinematics. It gives us 2 sets of ordinary differential equations for the position and orientation along the backbone as a function of curve length. We also use Koszorot static model. It's basically balance of forces for each element of the continuum media. Assuming linear Hooke's elasticity, we can rearrange it to find another 2 sets of ordinary differential equations for the strain and curvature along the backbone. We can use a numerical forward integrating scheme to solve this set of ordinary differential equations, and hence estimate the tip position and force based on the base force readings. For the tissue stiffness, we assume linear elasticity in the vertical and horizontal direction. If we assume the tissue is perfectly flat, we can use the estimated dip force and position to estimate the stiffness of the tissue. But if we assume the surface is irregular, we can use the estimated tip force and position from 2 different experiments to estimate the tissue elasticity. Later we can use that elasticity to find the tissue profile for each of the experiments. Here is a sample experimental run. Note the movement of the appendage tip on the stiff region. Here is sample experimental results. We can identify the contact of the appendage with the tissue based on the variation of the internal pressure and the values force sensor shows. Also, we can identify the stiff region based on the variation in the horizontal and vertical force values. You see the solid line, the estimation based on the base force reading, and the dashed line, the exact values based on the tip force sensor, showing good agreement. We consider 3 different probing scenarios. One is when the appendage is initially bent toward the slider motion. One when it is bent against the slider motion, and 1 while it's initially straight. Here are the results. On top, we have the estimated stiffness for each of the scenarios, and on the bottom, we have the average estimated stiffness in comparison to estimated value based on the tip force sensor, showing good accuracy. Summarizing that in a table, we can observe the smallest mean standard deviation and error for evaluating the force and stiffness in the horizontal direction when the appendage is bent against the slider motion, and also we see the smallest error and a mean standard deviation in the z direction when the appendage is bent toward the slider motion. So we suggest bend the appendage toward the slider motion if we want to have a better estimate of the vertical stiffness, and bend it against the slider motion if we want a better estimation in the horizontal direction. We also compare a rigid probe against our continuum probe. Here are the results. On the top, you see the results for the continuum probe, and on the bottom, you see the results for the rigid probe. On the left, it's the estimated profile, and on the right, its estimated stiffness. For the rigid probe, we can observe the important role of probe stiffness in terms of having a smaller mean standard deviation in estimating the profile itself. It also predicts 10 times higher stiffness value and mean standard deviation compared to the continuum probe. For the continuum probe, we can see the important role of probe compliance by observing 7 times a smaller mean standard deviation in estimating the stiffness value. It shows the filtering role of the compliance there. Finally, here it presents the estimated profile and estimated stiffness based on the continuum probe and the rigid probe. Top, it's the horizontal stiffness based on the continuum probe. It presents a comparison between the estimated stiffness based on the tip force sensor as the ground proof, and the estimated stiffness based on the base force sensor using our forward integrating scheme. You see that the location of the maximum stiffness is far from the nodule location. Middle is the vertical stiffness based on the continuum appendage, continuum probe. Here again we compare the stiffness estimated based on the tip force sensor as the ground proof, and observed stiffness based on the base force sensor. Here we see the peak location is on the nodule location, and in the at the bottom we have the profile and stiffness estimated based on the rigid probe. In the y direction and the z direction side by side, you see that the peak in the horizontal stiffness in the y direction is closer to the nodule location compared to the case of using a continuum appendage. But the peak of the vertical stiffness is on top of the nodule location. We can conclude that both probes are successful in predicting the location of the nodule. The rigid probe affects tissue during measurements, so we predict higher stiffness and profile variations. Also, it results in horizontal stiffness peak closer to the nodule location. The continuum probe less affects the tissue during palpation, so it estimates a smoother profile and stiffness values. Thank you for your attention.